History Physics. All right, let's talk about Newton's theory of gravity. This isn't just the law of gravity, universal law of gravitation, but the theory of gravity, which is a much broader set of ideas. Law of universal gravitation, right? And that's usually what we think of with Newton and we think of Newton's law of universal gravitation, which says any two objects with mass in the universe are attracted to each other. For instance, I got these sheets of paper and this pen are actually attracted to each other because they have mass. Everything in this room is attracted to me because I have mass, and everything in the room has mass. Right? The air is attracted to me. All air molecules are attracted to all other air molecules. But the thing is, we don't notice most of that. It wasn't obvious because you only notice it if at least one of the objects is really massive, right? And we usually only notice gravity. In this case, in our day-to-day lives, is we notice everything's attracted to the Earth. Right? Because the Earth is really massive. So at least one of the objects is massive. This pen would drop, right? I'm not going to drop it because then I have to pick it up. But it drops not because it's massive so much, but because the Earth is. The combination of the two of them have enough mass that we see an attraction. So any two objects, there'll be a force of gravity between them, and the force of gravity is a constant times the mass of the two objects divided by their separation squared. So if we had two objects, M1 and M2, right, and the distance between them is that. Now notice I drew that line from the center of masses because technically this only applies to point masses. It doesn't apply to things that extended objects. So what we do is we think about, if I shrunk this down so it was a point, it would be right at the center, and this would be at the center too. So the distance between them is from their center of masses. Now, it turns out, and Newton proved this with calculus, that as long as you have like uniform density, that you can just look at their center of mass and use this equation. This does apply to extended objects as long as you're outside the objects. Okay, you have to be outside the objects. We'll talk a little later about what happens inside the objects, which is also very interesting. So there you go. You got the law of universal gravitation. It's pretty easy to work with. The force is proportional to the product of the masses and inversely proportional to the distance between them squared. Now this is an inverse square relationship. And this occurs a lot in nature. And you can think about it like this. The reason it occurs often is because this has to do with like an expanding sphere. You could imagine if the gravitational field that's created is emanating from the Earth as a sphere, right? And you have so much gravity, and that sphere just keeps expanding like an expanding balloon. Now, the amount of gravity is the same, right? It's easier to understand with light, actually, because light behaves this way. If I had a light bulb, it's giving off so much light, and that light starts expanding. Well, anywhere in this expanse, it's the same number of photons that came out with original light, but now it's being spread over the surface of this expanding sphere. And we know that the surface area of a sphere is going to be 4 pi r squared. So the surface area of our sphere is going to be proportional to the radius squared. So light drops off with the distance squared. Sound, which also goes off in all directions, drops off with the distance squared. And so does gravity. It's an inverse square relationship, and that comes up frequently in nature, and it really has to do with the nature of the surface area of an expanding sphere. So we have the law of universal gravitation. I mean, we can plug into the formula and calculate forces. That's really not very difficult to do. But this is really good for proportional thinking. to exercise our proportional thinking. How can we calculate something that when we don't really have all the information we would want, right? And that's what Newton did, actually. He came up with this. He didn't know what big G was. It wasn't until the Cavendish experiment that they figured out what big G was. But using proportional thinking, he was able to see that this was indeed true. And with proportional thinking, if you calculate this with two different situations, the G will drop out. You don't really need to know G to answer certain questions. Now, let's do a problem with proportional thinking. And we'll do it where we don't quite have all the information we would want. So here's the problem. What applies a greater force of gravity? The sun on the moon or the earth on the moon? So we got the moon and it's experiencing gravity. Everything else in the universe, it's experiencing a force of gravity of the sun on it and the earth on it. Why don't you take a minute and again to draw a picture, look at the geometry and figure that all out and figure out what is which is a greater force and by how much, right? Let me give you some information that you're going to use. Mass of the sun is 1.99 times 10 to the 30 kilograms. Mass of the earth, 5.98 times 10 to the 24 kilograms. The distance between the earth and the sun is 1.50 times 10 to the 11th meters. And the distance between the earth and the moon is 3.84 times 10 to the 8th meters. What applies a greater force on the moon? The sun or earth? And then by how much? Right? And we can calculate that without actually knowing the mass of the moon. So why don't you take a minute and calculate that using proportional thinking, using our the Law of Universal Gravitation.
Pause the video now.
All right, so what I'm going to do is I'm going to say, all right, so I got the force of gravity of the first Earth. We'll go Earth on the moon. Force of gravity of the Earth of the moon equals G, mass of the Earth, mass of the moon, divided by the distance between the Earth and the moon. Right? And then we got the force of gravity of the sun on the moon equals G, mass of the sun, mass of the moon, divided by the distance between the sun and the moon. All right. Now, a couple things. Well, we know the mass of the moon, but if we divide these two relationships by each other, by going like that, we don't need G. We don't need the mass of the moon. Forgot to square those. That'd be square. It's an inverse square relationship. We just talked about that. So anyway, wait a second. I don't have the distance between the sun and the moon. Huh. I should have drew a picture. Let's see. Let me draw a picture. All right. So I got the sun. This is not to scale, by the way. I got the sun. And then I got the earth over here. And the moon is orbiting the earth. But where is the moon? Where is the moon? Because it's going around the earth like that, right? It's circling around. Is it here? Is it here? Is it here? Where is it? Where is it? Right? Well, for one thing, we'll see that the distance between the earth and the moon compared to the distance between the Earth and the Sun, or the Moon and the Sun, is quite small, right? The distance between the Earth and the Moon is 10 to the 8th meters, but the distance between the Earth and the Sun is 10 to the 11th. So it's significantly farther away. Plus, on average, where is the Moon? Well, it's kind of at the same distance as the Earth, right? Sometimes it's exactly about the same. It's exactly the same distance, and sometimes it's a little farther, sometimes it's a little closer, but not that much more. So on average, we can just use the distance between the Earth and the Sun, right? For the Sun and the Moon, because they're basically the same distance. So that's what we're going to do. So what do we end up with? We have the force of gravity, Earth-Moon, divided by force of gravity of Sun-Moon, equals mass of Earth divided by times the distance between the Sun and the Moon squared, which is the same thing as the Earth and the Moon squared, divided by the mass of the Sun, distance between the Earth and the Moon squared. Right? All right, just got to plug some numbers in. Oh, wait a second, that's not right. What do we got? Okay, well, I screwed up. So this is Earth-Moon. This should have been Earth-Sun. All right, I got 0.46. So basically, the force of gravity of Earth on the Moon equals 0.46 times the force of gravity of the Sun on the Moon. Right? So the Sun is applying about twice as much force on the Moon than the Earth is. So the question is, it kind of begs the question, well then why doesn't the Moon orbit the Sun? Right? Why is it orbiting the Earth if the Sun applies twice as much force as the Earth does on the Moon? And of course the answer is that the Moon is orbiting the Sun. It's orbiting both the Earth and the Sun, as you can see on this animation, right? It's doing both. In fact, everything in the solar system is orbiting the Sun, because it's like 99.9% of the mass of the solar system is in the Sun, or something like that. So everything, that's why it's called the solar system. That's how it got its name, right? Everything revolves around the Sun. All right, so there you go. So with proportional thinking, we could easily figure out the force of gravity on the Earth and the Moon is about 0.5 times the force of gravity of the Sun on the Moon. Yeah, right. Proportional thinking, right? That's a very valuable thing. That's something we could use quite a bit when we work with gravity. Something we use a lot when we work a lot of things, actually. So the theory of gravity has to do with, so we got the law of universal gravitation. Now the other one we have is the principle of equivalence. Is an important part of the theory of gravity. And remember when we were dealing with free fall stuff, we got this object free falling, right? There it is, a rock, and it's falling near the surface of the Earth. There's the surface of the Earth, and it's falling down. Circle the object of interest. Draw a free body diagram. I got the force of gravity down, right? That's the only force acting on it. So I applied Newton's second law. Sum of the forces equal mass times acceleration. Now, there's only one force on that, and that's force of gravity. Force of gravity is negative, equals mass times acceleration. And force of gravity was mg, equals ma. Right? And then we got, the acceleration is negative g, right? But the question comes up with, we have two masses in this equation, and those two masses do two very different things, right? We got this mass. What does this mass do? This is the inertial mass, right? This is the mass that makes something reluctant to change its motion, right? If it's sitting still, it wants to stay still, and the more mass it has, the more it wants to stay still, right? So this is inertial mass. That's what that does. It's just reluctant to move, right? Or change its motion. If it's already moving, it wants to keep moving. It's reluctant to stop then. So it's reluctant to change its motion. Now, what's this mass? That has nothing to do with inertia. What's this mass doing? It's pulling down. This is the weight mass, right? It's the mass that causes things to pull together, right? And then, so, oh, it's the same thing, right? It's not clear they're the same thing. They do very different things. Why do they both do both of these things? They're very different. And Newton said they are the same. And we've done sophisticated experiments since then, and it looks like they are. And Einstein kind of rolled it into his theory of relativity, and they figured out it's about the same. As far as we can tell with measurements, they're the same. So that is a principle of equivalence. Principle of equivalence. Right? That's another part of the theory of gravity. And finally, and it had to do with this one, was the Universal Law of Gravitation. Really, what was amazing about this was, in Newton's discovery, what he did was he noticed a falling object. You know, maybe it was an apple, maybe it wasn't. And he saw it fall towards the Earth. And then he saw the moon, and he realized the moon was in free fall around the Earth. So he said, wait a second. I bet that's the same reason. Which is was crazy at the time, because they used to think that the laws on Earth were different than the laws in the heavens, and the moon was clearly in the heavens. For instance, why does the moon keep going? Everything on Earth stops. Right? Everything on Earth stops. But everything up in the sky, like in the heavens, the stars and all, just seem to keep moving forever. They don't seem to stop. So that was that. So this was the universal law of gravitation. Newton said this applies everywhere. Right? There's another reason why the heavens seem to behave different, because they used to think the heavens had different rules because it seemed to behave differently. And he said, no, there's other reasons for that. But basically, the third was that his laws of motion were universal, that they applied everywhere, not just on Earth. That the three laws of motion applied everywhere. And, you can kind of see after that, it's like all the laws of nature apply everywhere. This was really huge, right? Right? Natural laws apply everywhere. They apply everywhere, right? So there's the theory of gravity, and that's probably the biggest one, right? We don't need a separate set of laws or different laws wherever you go. It's that the laws of nature are universal, right? That was huge. We don't think about that as huge now because we just assume that to be true because it's so well accepted. But at the time, it was not, right? It was not obvious. So, anyways, there's the theory of gravity, and all right. Let's dig a little deeper. Now, while we're here, we got that little G thing that we've already been using. Let's look a little deeper onto that. A little earlier in this, in our studies, if we wanted to calculate the weight of something, we knew its mass, we would use this relationship. We say, okay, the force of gravity equals the object's mass times G. And G was either called, it could be called the free fall acceleration, or sometimes called the acceleration due to gravity, or the gravitational field strength. So we're going to be looking at this as the gravitational field strength. And we would do that to calculate the weight of something. But if that's true, if I just got this battery and I know its mass, and I want to know what it weighs, I could just multiply it by G to get its weight. If that's true, and that's true, like for instance, if I wanted to calculate the weight of this battery and I knew its mass, what would I do? I could use this. I could just plug the mass in, and I know that G on the surface of the Earth is 9.8 meters per second squared. Or what I could do on this one is I go G, and now I have two objects, right? I got the Earth, and I got the battery. There's the battery sitting on the Earth. Right there, I got two objects. I drew my battery big. Battery's really not that big. If I were to draw the Earth, I wouldn't even be able to draw the battery. You wouldn't even see it, right? It's so small compared to the Earth. But I drew it big, you got to understand that my proportions aren't quite right there. But anyways, so what do? If I wanted to calculate the force between them, I would go, well, one of them was the mass of the battery, whatever that is, times the mass of the Earth, and we could look that up. Now, what are we going to use as the distance between them? If they are sitting on top of each other, isn't the distance zero? It's like, no, you got to remember, this only works for point masses. So what's the distance between them? Well, this battery really is right on the surface of the Earth, so I'm going to put it right there. And if I were to crush it down to a point, it would be right there. And if I were to crush the Earth down to the point, it would be there. So this is the distance between them. And I'm going to call that capital R. We usually use capital R to mean the radius of a planet or an asteroid or something like that, or a star. Capital R. And if a distance between two things, like if I had something out here, we would use, we would use lowercase r, right? So lowercase r has to do with just the distance between two objects, and we use uppercase usually to mean the radius of a planet, right? Or a star or something like that. All right, so this would be the radius of the Earth squared. If we wanted to calculate that, and we could look all those numbers up. So, and this is what you want to do. If this is true, and this is true, what's G? Right? If that's true, and that's true, in this case, this would be mass of the battery. If I was calculating that, what's little g made out of? How do I build little g? What's little g out of? We know what Fg equals mass of the battery, and I got the mass of the battery right there. So what must g be? Well, this must be g. Right there. That equals little g. The gravitational field strength equals the universal gravitation constant times the mass on the surface of the Earth equals the universal gravitation constant times the mass of the Earth divided by the radius of the Earth squared. And that will generally be the case. On the surface of the planet of Mars, it would be G, universal gravitation constant, times the mass of Mars divided by the radius of Mars squared, right? So you need to be able to figure this out easily. Not necessarily to be memorized, but you can figure it out pretty easily just by looking at this and universal relationship, and you should be able to figure out what G is. So in general, G equals big G times mass of planet or star or whatever big thing you're on divided by the radius of the planet or the star or the asteroid squared, right? So big G on the surface of some large celestial body equals G times the mass of the large celestial body divided by the radius of the large celestial body squared, right? All right, so that's little g, okay? And that's called the gravitational field strength. And in a non-rotating body, it's also the free fall acceleration. Now we saw in the unit on rotation, because the Earth's rotating, the free fall acceleration value is slightly different than this because of the spin of the Earth. Not much, but a little bit different. We're going to assume non-rotating bodies and not worried about the rotation, because usually that doesn't affect the free fall acceleration too significantly. All right, we're going to be using conservation of energy quite a bit when we study gravity. It's going to behave a little differently because, you know, when we studied conservation of energy before, we had some object. Here we go, I'll draw my thing again. So it was above the surface of the Earth. It was 10 feet in the air, 10 meters in the air, something like that. And it had a mass of 7 kilograms. You dropped it. How fast is it falling? So in that case, we would always set some place where we say, okay, the gravitational potential energy is 0 there maybe. You could set it anywhere, but we usually maybe say it's there. And let's say it was dropped from rest. And we want to know how fast it's going when it gets to the ground, right? How fast is it going then? And we'd use conservation of energy. We'd say the energy is 0 equals the energy at 1. And up top here, we had gravitational potential energy. And there was no kinetic energy because it started from rest. And maybe it was thrown down. But anyways, in this case, it would start from rest. Equals the kinetic energy at 1. And it has no gravitational potential energy because I said it was 0 there. And then we would say, okay, so the gravitational potential energy was mgh0. And that equals 1/2 mv1 squared, right? So, and that worked out nicely. We could easily calculate the speed of this object as it fell. We're not going to be able to do that now. The only reason this worked was because we were always dropping near the surface of the Earth. I don't care where you dropped it from. You were near the surface of the Earth. If you dropped it on the top of the tallest building in the world, you're still near the surface of the Earth. Or if you dropped it from the top of Mount Everest, and if somehow you could have dropped it straight down to sea level, you still were near the surface of the Earth. We need to keep these numbers in context. Because the radius of the Earth is, what we got? About 6,400 kilometers at the equator, right? So about 6 million meters is the radius of the Earth, right? 6 million of meters. Now, what's the tallest building on Earth? 830 meters, which is impressive, but it's nothing compared to that, right? Let's get this in meters, right? I was in kilometers. Let's go meters. Tallest building in the world is only 830 meters. Yeah, the height of Mount Everest is 9,000 meters. Again, nothing compared to 6,400,000 meters. So even our atmosphere is very small compared to the Earth. I had it written down somewhere. I don't know where I put it. The height of 3/4 of the mass of the atmosphere, because the atmosphere never really ends. It just kind of gets less and less. But the height of, if the height we would go to if we only had 3/4 left below us, is 11 kilometers, right? So even the atmosphere, you get the edge of the atmosphere, and you're really not high compared to the radius of the Earth. That's why the Earth looks flat, right? And in your reading, they had the flat Earth approximation, right? Why does the Earth look flat to us? Because it's so big compared to us, right? We don't see the curvature of the Earth. It just looks flat. We can do this as long as we have the flat Earth approximation, because even if you went on the top of Mount Everest, when we calculate G, which is G mass of Earth divided by R squared, radius of Earth plus radius of Everest, well, this doesn't change. If you add 8,000 to that, it doesn't change it significantly. So although technically the G on the top of Mount Everest is less, it's not worth mentioning, right? So we can use this value of G, and certainly to two significant figures, meters per second squared or newtons per kilogram, which is more appropriate for gravitational field strength, would be newtons per kilogram. That doesn't change appreciably, right? So that's going to be a problem. So we need to use a different approach. We can't use that the gravitational potential energy is just mgh. In your reading, they calculated the gravitational potential energy. And probably the most important idea with this is that we are no longer going to arbitrarily say this is the point of zero gravitational potential energy. We're going to establish one point that's going to apply for everything. And this will also come up when we study electricity, because we want that reference that doesn't change. And we're going to set the point of zero gravitational potential energy when two things are infinitely far away. When they're infinitely far away, the gravitational potential energy is zero. So we got two masses, M1 and M2. And when M2 is at infinity, we say, here's infinity out here. I know it's not quite infinity, but it's as infinite as I can get on this board. I'm going to say UG equals 0. Gravitational potential energy is 0 at position infinity. So what does that tell us about if I move it to here? So that mass 2 is here. Now mass 2 is here. What do I know about the gravitational potential energy between these two? Remember, gravitational potential energy is between two objects. It's not just this thing. It's the gravitational potential energy between them. So if that's 0, that's as large as it can be, right? Because as it gets closer, it's going to have less potential energy, right? And when it gets real close, it's really small. There's a point at which when it's as close as it can be, that's as small as it can be. So if that's 0, then all is negative. All gravitational potential energy is negative or 0 when it's at position infinity is 0. You can't have a positive gravitational potential energy because we're defining as 0 at position infinity. That's an important idea. And mathematically, they calculated the work, and you can look that up. I'm not going to spend the time to do that right now. The gravitational potential energy of two objects, two stars, two anything, or actually you could have multiple, or between two, is going to be G M1 M2 divided by the distance between them, and it is negative. Right? So at this position R, right, the gravitational potential energy is minus G M1 M2 divided by R. Not squared. You gotta be careful. It's not squared now. It looks a lot like the universal gravitation relationship, but it's not squared, and it's negative. All right, so there we go. So why don't we try a problem where we use that. In our book, they had a question. Okay, this is question 41 in your textbook. Two Jupiter-sized planets are released from rest 1.0 times 10 to the 11th meters apart. What are their speeds as they crash together? All right, so they're Jupiter-sized, and I guess the distance between them is 1.0 times. I don't think I'm going to calculate any numbers. Let me just show you how to do this problem. And you can plug the numbers in and check. All right, so I got Jupiter and I got Jupiter. Right? And they got a radius R each one, and it's a radius of Jupiter. And you can look all that stuff up. That's in your textbook. They got a chart, all that stuff. And they're separated by... All right, I assume this distance is between their center of masses. Not that it's going to matter because that's 10 to the 11th. But anyway, so they're this distance R between their centers of masses. And how fast are they going when they crash, right? So this will be time 0, and then at time 1 is when they crash together. Right? Like that. All right, so they're going to be flying together like that. Boom. Like that. How fast are they going? How fast is each one of those going? All right. So, and that's time 1, right when they crash together. So, I'm going to say now mechanical energy is conserved here. We're in space, so there's no friction or anything like that. So the Energy at 0 equals the energy at 1. All right. Well, what kind of energy do we have? Well, it looks like we have gravitational potential energy. It's not 0 because they're not infinitely far apart. So I got the gravitational potential energy between these two, right? Keep in mind, gravitational potential energy, we didn't often think about that before. When we looked at a falling object, we didn't talk about that the gravitational potential energy was between the Earth and the object too often, but it was. It was between the Earth and that was the potential energy. It was between the two of them. You couldn't have potential energy with just the object, right? So this is between the two objects. So the gravitational potential energy between them equals. Do they have gravitational potential energy when they're together? Sure. They're not infinitely far apart, so gravitational potential energy at 1. And do they have kinetic energy? Yes, they do. In fact, there's two kinetic energies, right? Because they're both moving, right? So I will say plus, call that Jupiter A and Jupiter B. Kinetic energy 1 of A plus the kinetic energy 1 of B. They both have kinetic energy, so I better take that into account. Gotta do that. All right. So what do we got here? We got minus G, mass of Jupiter squared, because they're the same mass. Mass of Jupiter A is the same as mass of Jupiter B. Divided by, how far apart were they? R, not squared. You got to be careful with that. It's easy to square that, right? You're used to squaring with the universal gravitation constant, and that looks like it, but, with the universal law of gravitation, but we don't square that. So be aware of that. That's a common mistake. Minus G, mass of Jupiter squared. Now, how far apart are they when they smash together? Can't be 0, right? They can only get as close as... Now, this does get tricky, I gotta say. We're gonna assume that the planets don't... Well, number one, Jupiter's a gas. Even if it was solid, when they hit, they would melt. And I don't know, how close do they get together? Well, the best we can do is how fast are they going right as their surfaces touch. So the distance between them is going to be 2 radius of Jupiter squared, right? Because we got R and we got R. So their center of masses are 2R apart squared. All right. Plus 1/2 mass of Jupiter, VA squared, I guess, and then plus 1/2 mass of Jupiter, VB squared. These are going to be the same. I could just say V. I could just say V. Probably call it V1. They're going to be going the same speed. And then we would just solve that, right? So we got 1/2 of 1. That's just 1. So let's see. We can get rid of... we got a lot of mass of Jupiters that can go away. Let's see. Boom, 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 boom. And that's probably about it. So what do we have? We have G, mass of Jupiter, 1/4RJ squared minus 1/... that's not squared. That's not squared. Why did I square that? See? I already made that mistake. That's not squared. That's not squared. It's not squared. It's not squared. So that's not squared. Yeah, that's not squared. That's not squared. Right? I think that's right. I factored out the G and the MJ because they both had that. This one's negative. That one's positive. Equals V1 squared. All right, so you can plug your numbers in, and we should be good. Let's see, we don't get a negative value, do we? I don't think we do. Okay, that's a big number. So that's a small number, and that's a bigger number. That's going to be, this is smaller than that. Therefore, this whole value is bigger, so we got positive. All right, good. I hate it when you get negative numbers in the radical. In a situation like that, that means you made a mistake. It doesn't always, but in this case it does. All right, let's do one more problem with Jupiter. Then I'll call it a day for this particular lesson. And that has to do with escape velocity. If you were to launch a rocket from the surface of Jupiter, now this isn't a rocket that is like burning fuel, that's constantly, the forces are changing. Let's say you got this spring rocket where you're going to go doink, and you're going to send it up. How fast do you need to send that thing straight up so that it will never come back to Jupiter? I want the minimum speed. So you go doink, and it goes straight out and never comes back to Jupiter. So I got Jupiter here, and I got my rocket on the surface of Jupiter, right? So that's 0. And then at 1, I want the rocket, the rocket went fast enough that it's never coming back. Now, it doesn't have any fuel, so it's just gliding. It's got to glide. You go doink and go zing, and you gave it enough doink that it's not coming back. So, this is a conservation of energy problem. So, let's take a look. And what do we need to realize to solve this problem? The important conceptual thing occurs here. How do we know it's not coming back? Under what conditions is it not coming back? Because gravity, if something stops, gravity is always going to pull it back. Is there a place where gravity can't pull it back? Yes, there is. That would be at infinity. At infinity, gravity can't pull that back. So position 1 is at infinity. Now, if I'm going to launch that at the minimum speed to do this, how fast is it going when it gets to infinity? When it gets there? How fast is it going? And the answer is 0. V1 equals 0. Because if it makes it to infinity and it's still moving, that means it has more energy than it needed. It didn't need that much energy to leave, right? So it stopped. It has no kinetic energy, and it's at position infinity. So how do we solve this problem? We know this is conservation of energy. Energy at 0 equals the energy at 1. All right, what kind of energy does it have at 0? Well, it definitely has gravitational potential energy. It's not at position infinity yet. And it better have kinetic energy, because that's what we want to know. How fast we got to send that sucker, right? So the gravitational potential energy at 0 plus the kinetic energy at 0 equals what? Well, what's the gravitational potential energy here? It's 0, right? It's 0. It made it to infinity. And how fast is it going? 0 speed. So what's its kinetic energy? 0. So this will only escape and never come back if its total energy is 0. Right? Total energy has to be 0. And we say that at that time it's unbound. This thing is unbound. It can escape, right? If it had more energy, it would still escape. But this is the minimum speed to be unbound by Jupiter. Now in this problem, we're ignoring the sun, which is quite a thing to ignore. But let's just say Jupiter is the only thing around, right? Just to simplify the problem, because you really can't, ignore the sun. But anyways, so here we go. So we go minus G, mass of Jupiter, mass of rocket, divided by radius of Jupiter, plus 1/2 mv0 squared of the rocket equals 0. All right, this is rocket. Mass of the rocket goes away, and we end up with V0 squared equals 2g mass of Jupiter divided by radius of Jupiter. So let's get rid of the square and square root that. So there you go. That's called the escape velocity. So it would be 2g mass of Jupiter, radius of Jupiter. And that will generally be the case. You won't always have Jupiter in there, but you should always get something of that form if you just want to figure out how fast would it need to go to escape the gravitational influence of that celestial object. All right. All right, that's all I got for you today. I'll catch you later.
Extreme fandom.